Welcome everybody. This is a must-do problem. Take a look at this beautiful photo. I saw this in the back of the book, 2D kinematic motion problem, and it looks amazing. This is a must try. We gotta do this. And I'm gonna rip it off the dome. We're not gonna use any solution manual, no AI, none of this crazy stuff, guys. We're gonna go straight from the thinker and solve this problem, no matter how long it takes. An enemy ship is on the east side of a mountain island, as shown in figure this one below. The enemy ship has maneuvered to within 2,500 meters of the 1,800-meter high mountain peak and can shoot projectiles with an initial speed of 250 meters per second. If the western shoreline is horizontally 300 meters from the peak, what are the distances from the western shore at which a ship can be safe from the bombardment of the enemy ship? An amazing problem, guys. This gets my blood boiling. I am hyped. I'm ready to tackle this problem. I think we got all the knowledge we need just in our forefront mind right now. We've been doing some problems with kinematic motion, so we know the motion that these objects follow. And we are pretty good with vectors. And we know SOHCAHTOA and Pythagorean theorem. I think we're chilling. We're going to try it out. First, I'm going to just think with you guys. We're not going to write anything. I'm just going to think about what this problem is asking me. So I'm going to reread the last sentence, or the last two sentences. If the western shoreline is horizontally 300 meters from the peak, which is shown over here in the image, what are the distances from the western shore at which a ship can be safe from the enemy attack? Okay, so the cliff ends 300 meters from where its peak is located with respect to the x-axis. After 300 meters, the boat only has a specific amount of room where it is safe from the trajectory shown on screen, the white trajectory here, before it reaches a specific distance where this enemy ship is going to hit us. So this enemy ship shoots something at a theta h with this initial velocity. It travels and just crosses the mountain, and then it hits over here. So there is a distance over here, some distance d. We don't know. We could call it x. We can call it question mark. We can call it d. It doesn't matter. This is what the question is asking us for. So at what distances from the western shore? And the western shore is this point right here, right? Yeah, and it says distances like plural. But I think if we find the maximum distance that the projectile here can land at and safely cross here, then this will be the no-go zone, and anything beyond this point is the no-go zone. So anything within this point here is the safe zone, and I think that will answer this question for distances. So this is a little bit crazy, but you can see these nice parabolas that the book has drawn for us. This is what caught my attention at first. You can see both of these projectiles, they're at different angles, right? You can see them here, but they both just cross the tip of this mountain. So it could either shoot really far all the way there with a low angle, or it can shoot kind of high and just cross here. So I'm imagining if it shoots it too high, right, it's going to do something like this, and it's not even going to like cross the mountain. So there's a sweet angle. Maybe the sweet angle is this one that it showed us, right? So this is the low angle. If it goes below this, it's probably going to hit somewhere here. And this is the high angle. If it goes above this, it's probably going to go something like that, you know what I mean, and not cross it. This is just what I'm guessing. So what I'm thinking is if we find this high angle and then we use some kinematic equations to find where this thing lands, then we can use this as the spot and be like, okay, from the shoreline up to this x, you are safe. So you could stay within here. We can call this d, distance d, and then that will give us a solid answer. But this is tough. This is tough. Anywho, I've just thought about the problem for like 5 minutes. Getting acquainted with it, thinking of some ideas. It's pretty important to have a game plan before you start attacking the problem, because if you just quickly start attacking the problem, you might be on the right path, but you might also make an error. And later down, you'll be like, damn, I wasted all this time when I could have gone down this other path that was much faster, much simpler. So it's good to just spend a bit of time at the beginning of the problem, assess, figure out what we got to do. And we're going to use x and y kinematic equations, try to find this theta h, and try to find where the projectile lands. So let's start off with a projectile. In the x direction, it has constant velocity, Vx initial. So after the ship fires it, it fires it at some direction here, some theta, whatever, with this total magnitude velocity or speed. So that's the length of this vector. If I want to decompose this vector into its x and y components, so this is the velocity initially in the y direction, and this is the velocity initially in the x direction. We could take this here and then put it in our x component equation, and we could take this here and put it in our y component equation. And then using those two and some other stuff, maybe we could figure out what time and what distance this thing lands at. So that is what we're gonna slam. And what is happening in the x direction is constant velocity, so we can pull up the constant velocity equation for position, which is Vxi times t, constant velocity times time, plus the initial position. I guess we can figure out what Vix is. So if we take a look at this triangle, Vix is over here, and this angle is theta h, Vix. So if we have adjacent and hypotenuse, we have cosine over here. So what we can do is Vi, this is the initial vector. It's 250 meters per second, so we could just plug that in. And here we multiply by cosine of theta h. We don't know what theta h is, but let's call it theta high, the highest angle that will possibly cross this mountain here. So this is something I was thinking about before. Obviously, a low angle is going to be very far from hitting the ship if the ship is hiding right here, right? This is going to go all the way over there. You're completely missing him. But if you go at the maximum high angle, you just cross here and then you get very close to hitting the ship. So this high angle, I'm treating it as like the perfect angle that this ship can fire at, such that it hits as close as possible to this little region here, the safety region. So if it hits very close, it has a higher chance of hitting the ship. But this ship, if it knows this number, it knows to hide within some safety zone, which is what we're trying to find here. So I have Vix, and how do we create our coordinate system here? So I'm asking the coordinate system because I need to know the initial position of our projectile. Let's say it's some cannonball. If I set up the y-axis here and the x-axis like this, right? There's some points of interest on the x-axis here, here, here. But then this point right here, xi would be 0. So this is a preferable system to choose, coordinate system, because if I choose the coordinate system to be here, then x initial is not going to be 0. It's going to be like negative, I don't know, 2,500. So I'm just choosing this coordinate system because it gives me a 0 and it's going to be clean. Also, when we do the y coordinate is also 0. So it just simplifies things a little bit. But you could choose whatever coordinate system you want, just be consistent. So that being said, we're going to use this equation here and say x of t is equal to 250. I'm going to keep the units here. Cosine theta h, we don't know what theta h is, plus 0. So this is an important equation. We're going to put this in pink. I don't know what to do with it yet, but I've developed it, and that tells me the position on the x-axis as a function of... Wait a second, we forgot time. Hold up, guys. Made a little bit of mistake here. This is times time. So over here, we have times time. So yeah, I plug in time and I get the x position. Let's do the same thing for the y. We have y over here. So y as a function of time depends on the initial y coordinate, which is 0, the initial y velocity times time, and also the acceleration due to gravity. We've seen in previous problems that it's pretty beneficial to have negative g as the acceleration here. I'm going to do negative g t squared, and g is 9.81 meters per second squared with a negative sign in front of it. So let's replace everything that we know of in this equation. Y initial is 0. VIY, we could do the same thing as this equation, So VIY is 250 meters per second times sine. And this is just from the Pythagorean, or sorry, the SOHCAHTOA. So this is the y component of this vector, right? I take this angle theta h, and I can create this right angle triangle over here. And if I find this component of the right angle triangle, that is exactly the same as the VIY. It's the same thing as the VIX. All right, now we can replace this. So 250 meters per second times sine theta h times time minus 1 over 2 times 9.8 meters per second squared times t squared. Another interesting equation, which is for sure useful, so I'm going to put a box around it like this. Put a box like that. All right, now what can we do with this? Well, at this stage, we've developed the equations for our projectile along this path here, right? I've specifically chosen this path because I used theta h over here. So this theta h is going to give me this projectile. Whatever theta h is, at the end we can plug in theta I, but I'm going to specifically look at this trajectory because I think this one is going to give us the answer to the problem. From what I said before, like hitting this little area here. All right, so we have a few interesting points. We actually have one interesting point. We know that exactly over here at x equals 2,500 meters and y equals 1,800 meters, it will be right here. So we have one data point that we can put into here and one data point that we can put into here, right? The x point can go here and this can go here. And then what can we get? I guess we can pull time out of that. Or, well, I guess time is also equal here. Time equals time. So from this equation, the t equals here because it's at this point at the same time, right? It's at this x coordinate and this y coordinate at the same time. So I guess if we have everything here, the only unknown is theta h. Theta h, and yeah, we have t. So yeah, I'm just kind of trying to see how we could solve this. If we find theta h, what would be valuable about that? I'm kind of thinking ahead, like I said before, so I don't like enter some kind of corner that I have to work back from. So I'm just trying to think of how theta h is going to be useful. Well, if we find theta h, I see. Hear me out, guys. If we find theta h, then the position equations are completely known to us. So currently the only unknown is theta h. That is missing here and here. If we know what theta h is, then we can find the x position as a function of time. So if we find what time the thing lands over here, then we can plug that time into here and then pull out the x position of this thing. And then our answer will just be, oh, from this point here, which is 1200, 2500 plus 300 meters from x equals 0. From this point all the way to this point, which again we pull out from here, that is the safe zone. And how we can get that is we look at this trajectory and we say, when does y equal 0? So y equals 0 at two places, here and here. Then we can take this piece of information, so y equals 0. What time does this happen at? We take y equals 0, plug it into here. Since we found theta high from before, the only unknown becomes the time, and that is the time where this thing lands. And from that time, we can plug it into here and get our answer. Do you guys see how I'm thinking about this? So just a little bit of a pathway. I don't see any issues with this, so since I don't see any issues, I see a clear path towards the answer. I'm gonna just push through. We might run into something, or we might, I don't know, at the end see that this is a weird answer and it's wrong, so we're going to go back and reassess. But so far I have an idea. So how do we find theta high? I guess go back and use this point here. Let me actually write down what this point is. It is 2,500 meters on the x-axis. Oops. 2,500 meters on the x-axis 1800 meters on the y-axis. So what I did here to save some time is I just copied our x equation and our y equation over here, which we found from before. I took this data point, which we got from here, and then I plug in 2500 into this equation, 2500 into the x equation, and I isolate for time. So I just divide both sides by this thing, and I get, had a little flipper there. I isolate for time, so I take this, divide it on both sides, and I get 2500 meters over 250 meters per second times this. Now I've isolated for t. I'm just going to do the exact same thing, plug this data point into the y, isolate for t. Isolating for t here is going to be a bit weird because we have t and t squared. But one thing I could see that we could do is we already have a value for t. So instead of equating the t's, we could just take this t, this value of t here, and plug it in here and plug it in here. Then t is effectively removed from the equation. We have cosine theta h here, sine theta h here, and this y is equal to this. So we could just simplify. I'm actually going to do that right now. Okay, so I ran out of room almost, but basically what you see over here is the y equation. I've just replaced the y value for this one over here, right? Replace that right here. Boom. Everything else stays the same. This is 250, this 250, sine h, and then here is t. I just replace inside t what we got from the x equation. This is substitution. We're trying to eliminate a variable so we can solve and find the other unknown. In this case, the only unknown is this theta h. Then I have the rest of the equation here, negative 1/2, 9.8. I added a 1 here, there's no 1 here. Sig figs, it doesn't matter too much. And then here, t squared, I just put the same thing that we got from here and square it. And I also didn't write units here just because it was getting a little cramped. Now, it is a little bit interesting what's going to happen here. So check it out. We have a 250 here. It is being divided by a 250 here. We have a sine theta h over cosine theta h, which can turn into a tangent theta h. But then over here, some messy stuff is happening because we have cosine theta h in the denominator and it's squared. So this is going to get tricky because we have two trigonometric functions inside one equation. It's a little messy. Like, I don't know if I've dealt with this before. So let's simplify it and then see if it looks as bad as I think it will. Okay, so I did a few things here. Basically, I canceled this guy with this guy, so all that's left is 2500 meters. Sine over cosine is tangent. But then over here, a few more things happen. So I applied the square to both this and this 250, and then multiplied whatever I got here with this 9.81 and with this negative 1/2. What I got is 490. And I also did some unit analysis. These are the units for here, and I get second squared, and then second squared pops out over here, and the units over here are meters. So this is in meters. So that looks good because check this out. We have meters on the left-hand side, meters over here. Tangent of theta gives you a unitless quantity. So everything in this first term is meters. Then over here we get 490 meters times this 1 over cosine theta h squared, which is from over here, right? I apply the square over here, and this is what's left over. This is still a unitless quantity, and meters over here. So we can subtract meters and meters, and what we get is meters. So at least the units check out, but this is where the problem starts. I don't know how to solve this at all. I'll be real with you guys. There's a tangent theta here, and there's a 1 over cosine theta here. We have to find the theta for which this equation is true. I don't know how to do this at all. The best guess I have is to just plug theta and see if something is true, but that's going to take forever. Honestly, I don't know how to solve this problem from just my knowledge. I'm going to have to check out how to solve something like this, or just plug it into ChatGPT and be like, what is theta h? So if I get to this stage where something is unsolvable with my current knowledge, I'm a little bit skeptical if I should push through, because these problems, yeah, they're challenging. I think this is the last problem in chapter 4 of the Survey and Joa book, but I don't know if they're going to ask you for this strange trig algebra. You are supposed to know some trig. I thought just knowing the SOHCAHTOA and Pythagorean theorem was going to be enough. Maybe there's an easy way to solve this trig identity if you brush up on some trigonometry, but right now I'm not sure. So what I'm going to do is just put this into Google or Wolfram Alpha or ChatGPT or anything like this, see if I get theta, and plug that theta in and see what answer we get. And then if I have no other solutions, I'm just going to check the solution in the book, see if it makes sense with mine, and we're going to accept that this trigonometric identity is a roadblock for future problems. This is a tough problem. I'm probably 90% certain that you guys are not going to see something like this in a final exam. This is a math problem. You don't need to solve this to be good at physics. So yeah, if you ever see something like this in a final exam, just ask the professor and be like, bro, I don't know how to solve this. Can you help me? If he doesn't help you, honestly, guess what theta is. From the picture, just be like, yeah, it's not 90 degrees, it's not 45 degrees, it's somewhere in the middle, 50, 60 degrees, whatever. Pick that, solve the problem. You're going to lose some marks, but you're going to be chilling. Don't leave anything blank on the exam. All right, I'm going to plug this in, let you guys know what I see. All right, guys, interesting information. So I learned that cosine of theta 1 over this is equal to secant of theta. And there's this identity, which is secant squared of theta is equal to 1 plus tangent squared of theta. So basically, you can replace this 1 over cosine in here for secant, and then this secant becomes squared, and you can use this equation, replace that entire secant with 1 plus tangent, so this becomes 1 plus tangent, and then you have tangent, and this tangent is to the power of 1, this tangent is to the power of 2, so now you have like a quadratic formula. Just replace the tangent with the x, and then you will get an answer for tangent of theta, and you can do tangent inverse to find the angles. So I use some language model to get these angles. I don't know if they're right, but for the purpose of just getting this problem done physics wise, I'm gonna write them here, and maybe if it's useful, we'll go back and brush up on some trigonometric identities and some Pythagorean theorem and substitutions and all that. But these angles feel weird to me, I'll be real. First of all, it's from a language model, so I don't know if I trust them 100%. Second of all, both of them look like they're in the range over here. So in a quadratic formula, which is what we got from this when we replaced the 1 over cosine with secant and then turn everything to tangent, we get two values. But they both look like they're in here, so maybe around here is 45. Just after that is 50. And then between 45 and 90 is 22.5 plus 45. Oh my god. So what I'm thinking here is, let's draw this 90-degree angle. Right in the middle of that is 45 degrees. In the middle of this is 45 plus 22.5, which is 67.5 degrees. And our angle is right between that. So 22.5 divided by 2, 11.25 plus 45, that's 56. So this thing looks like it's at around 55 or 56 degrees. I'm honestly just spitballing, but damn, brother. It looks like both of these values. So what happened here, check out how we set up this problem. Once we got our kinematic equations, we plug this value in, which is going to say, okay, our projectile is going to hit exactly this thing, this part is going to hit it here. And what we saw was it happens at two different angles. But I'm not sure if these are the angles that they're talking about. Because this angle here, this theta low, does not look like the smaller of these two, 50 degrees. It's definitely not that. Oh, this is a tough problem, bro. I don't know if you guys have the same confusion I do here, but you know what? I'm going to go back and double check these values with Wolfram Alpha or something more powerful. All right, guys, I couldn't really find an answer. I was trying to use Symbolab, but it wasn't working. I'm a little too lazy to go through the math on my own. What I'm going to believe right now is that these angles are correct, this 50 and 75, and they do correspond to these two angles, this theta h and theta l, because both of these trajectories, if you see, they lead us to the same point. So when we were doing our calculation, the math didn't really know we were taking this trajectory or this trajectory. The math just knows there's two possible trajectories that lead to the projectile being here at the same time, and that's at this angle and this angle. What I'm going to force myself to believe right now is that this picture is not drawn to scale, because if it was drawn to scale, then these angles do not look like these angles that we got from the math. So sometimes this could be the case. It's very annoying, and it's just a guess I'm making. I could be wrong about this, but I think before looking at a solution to this and like really making sure we're doing something correct, I'm gonna just push through with the angles that we got here. I'm gonna take the L on the solution to this kinematic equation and just accept that ChatGPT answer of this. And we're going to go through and we're going to see if we get something useful. This is the same thing as just guessing an angle. If you're in an exam and you can't use AI or you can't solve for this, just guess an angle and then continue with the problem. So that is my tip for you guys. Let's use this. And I guess let's pick the high angle, 75, and plug it into these two equations. So what I'm going to do now is actually simplify this entire thing. So I just checked cosine of 75.64 is equal to 0.248. I'm going to multiply that by 250, and we get 62 exactly. So everything over here, I'm just going to replace by, actually, I'm going to replace by 62 times t. And the units here are, I guess, important. We have meters per second times t. I'm going to do the same thing over here. So we have a sine of 75.64. We're going to multiply that by 250, and we get 242.2. Then here we have 0.5 times 9.81, and the time stays as is. Minus 4.9 times t squared. So just simplify the equations plugged in. Now it's amazing. We have the equation of motion for the projectile at this large angle. Now what we could do is say, okay, we're going to set y at t final is equal to 0. So the projectile hits the water over here. And this is happening at t final. We're going to use this equation and just solve for t final. So here we have 242.2 meters per second times t minus 4.9 meters per second squared times t squared. All right, I can factor out a t over here. So I have t is equal to 242.2 minus 4.9 t is equal to 0. So when is this entire equation equal to 0? It's equal to 0 when t is equal to 0, right here, which makes sense because y equals 0 at t equals 0, so that makes sense as a solution. But the other time is it's equal to 0 is if this entire thing in the brackets equals 0. And when that equals 0, we see that 4.9t is equal to 242.2. So t is equal to 242.2. I think that's meters per second. And then you divide it by meters per second squared. So you should get the final answer here in seconds, if I'm not mistaken. So this is the time it takes for the projectile to land in the water. Now we can take this and just plug it into this x position and see where it lands. X at t final is equal to 62 meters per second times 49.429 seconds. The seconds cancel, leaving us with meters, which looks great. And what we get is 62 times 49.429. We get 3,000. This is looking good. 064.6 meters. And this is our final answer. Let's put this in green. 3,064 meters. Let's see if this actually makes sense. So here's 2,500 meters from 0 all the way to the middle of the mountain, plus another 300 is 2,800, and then the ball lands at around 3,000. So from 2,800 to 3,064 or whatever it was, this is the safe range for the boat. Now, is this true? I'm going to check my solution manual. All right, so I'm looking at the solution, and it looks like we did get the same values for the angles. Thank you, ChatGPT. So the low angle is actually 50.1 degrees, and the high angle is the 75.6. Then they plug it into the range equation, and they see that it is 3,070. So they round this a little bit up. 3,070 meters is where the cannonball lands. But then they quote the distance in meters. So I said from 2,800 over here, 2,800 all the way to 3,064. Instead of saying this range, they just do 3,064 minus 2,800. So their final answer is 270 meters or less. Oh, but they do something cool as well. They actually calculate this over here, and they see where the projectile lands over there, and then they quote that distance, and then they say, okay, if you go further than that distance, it's also safe. So closer than this distance is safe. Everywhere here is X. Wherever this projectile lands over there in the distance, after that distance, it's also safe. I'm not going to do that because I think we've already kind of pulled out all the cool info from this problem. I think it's an amazing problem. As you guys saw, I was struggling with quite a lot of it. But try to do the same problem. Try to just go in the back of the book. Like I saw this, I was like, whoa, battleships, this is interesting. You guys can find something similar, an interesting problem. There's many of them in the book. There's basketball problems, there's football problems, there's something with lasers. I don't know, you guys can take a look. This one was interesting. Try to do it on your own and see if you can solve this trigonometric thing that threw me around. And yeah, let me know if you guys are enjoying these problems and if you want to see specific problems. As always, keep studying, keep grinding, stay hydrated, talk to some friends and family when you get into a pickle. Maybe they'll be able to help you with a problem like this. And I'll see you guys in the next video. Thank you very much. Peace.